Okay, so my YouTube is up and running. All right. So I was saying that if you missed the last class, you can basically watch the YouTube video. Oh, hold on 1 minute. Okay, I'm sorry about that. Yes, so the YouTube video is located. Okay, hold on. In Canvas, if you go to the module section, right here, and then you can click on the link provided here. So it's under this folder right here, CHM 2045 Spring 21. And this here represents what we covered the last class on Thursday. So you can catch up on, we didn't cover much in the lecture. Basically what I did was go over the syllabus and then I started with chapter 1. And as I said then, chapter 1 through 5 is pretty much a review of what you did in introductory chemistry. So you won't be missing much in that regard. So that's basically where you can find the video. So like today's video will be posted there as well for those of you who are, who want to rewatch the video, or if you miss a class and you want to watch a video, you can go there to get it. Okay, so what I'm going to do is proceed from where we left off the last time. So let me move this up here. And let me make this full screen. Okay, and let me minimize this here, get this out of the way. Okay, so we talked about matter the last time, and if you remember anything from your introductory chemistry course, you'll know that matter is anything that has mass and volume, right? Anything that has mass and volume, that's matter, right? So it's all the material stuff that exists in the universe. Now, we can categorize matter into two categories. We have what are known as pure substances, and then we have what are known as mixtures, right? Now, under pure substances, we have two subcategories. We have elements and compounds. We're going to talk about the difference between these two shortly. And on the mixtures, that itself can be divided into two subcategories, homogeneous and heterogeneous mixtures. Okay, so let's talk about the difference between elements and compounds, right? Elements are basically substances that cannot be, well, firstly, let's talk about substances first. A substance is basically a type of matter that has a fixed composition that does not vary from sample to sample, all right? So for example, H2O is a pure substance because water has two components, hydrogen and oxygen. And if I remember correctly, oxygen is about 88% by mass of water, and hydrogen is about 11 or 12% by mass hydrogen. And that is fixed for water, right? If you have a substance which contains hydrogen and oxygen and the percentages are different, then you know that's not water, because for water, those percentages are fixed, all right? So that's a pure substance. That's what pure substances are. Their compositions remain fixed. Now, under that category of substance, we have two subcategories, as I said before. We have elements, which are substances that cannot be broken down into simpler substances by chemical means. And this is very important, by chemical means, because you can actually break down elements into simpler elements, but that would not be a chemical reaction. That would what we would call a nuclear reaction. And for those of you who plan to do general chemistry 2, there'll be a whole chapter dealing with nuclear reactions that you'll see where this takes place, where you can actually have the conversion of one element into another element by breaking down the nucleus using different particles and so on. I won't get into that right now, because that's for general chemistry 2. But basically, elements are substances that cannot be broken down into simpler substances by chemical reactions. And then we have compounds, and compounds are basically substances that can be broken down into simpler substances, right? And as stated here, here's another definition. It's basically a substance that is made up of atoms of 2 or more elements with the different kinds of atoms combined in fixed proportions. So water, for example, is a compound because it is made up of 2 elements and the proportions are fixed. An element would be something like oxygen or nitrogen or carbon. all those elements that you see in the periodic table, because those elements, those substances cannot be broken down into simpler substances. They're just made up of one type of atom, all right? So that's the difference between elements and compounds. So let's look at the other side where we were talking about mixtures, right? So let's define what we mean by the term mixture. A mixture is basically a physical combination of two or more substances. And one difference between a mixture and a pure substance is that a mixture does not have a fixed proportions of the different components that make up the mixture, right? So if you have, for example, a mixture of, let's say, ethanol and water, well, it could be a 50-50 mixture, or you could have 25 grams of water with 75 grams of ethanol, or vice versa. In fact, you literally can have an infinite number of possible composition ranges, all right, when it comes to a mixture, okay? So when it comes to mixtures, there are two types. You have what are known as a homogeneous mixture, otherwise known as a solution. And basically, that type of mixture is one where the composition is the same throughout, right? So a good example of a homogeneous mixture would be ethanol and water, all right? Because if you mix ethanol and water and make sure that it all stirs up, what you'll find is that it doesn't matter if you look at the bottom, middle, or top part of that solution, the composition of the two substances would be the same, all right? Now, I have a question for you. Can you think of any other examples of a homogeneous mixture? Any other examples? Anybody?
Salt water.
I'm sorry?
Salt water.
Okay, salt water, salt and water. I would agree with that. Any other examples you can think of? I'm sorry, I can't hear you. You sound like you're far away. Oh, let me check something out here. Oh, somebody said something in the chat. Okay, let me see. Kool-Aid, okay, I would agree with that. Yeah, Kool-Aid is another example of a homogeneous mixture. I'm assuming you're talking about Kool-Aid where you actually add the mix to the water and then you'd stir to dissolve, all right? So assuming that to be true, then yes, I would agree with you. Any other examples you can think of? Let me make it a bit of a challenge. Any other examples that do not include water you can think of? Any example of a homogeneous mixture that does not necessarily include water? Well, come on, folks, it's not a difficult question. I'm quite sure you can think of an example from your everyday lives. Okay, what about the gasoline that we put in our cars, right? That is an example of a homogeneous mixture because gasoline is basically a mixture of a group of compounds we call hydrocarbons, all right? So that's an example of a homogeneous mixture. Can you think of another example of a homogeneous mixture? Well, okay, let me give another example of a homogeneous mixture. The air we breathe is an example of a homogeneous mixture because the air we breathe contains several gases, the major component of which is nitrogen, which is, if I remember correctly, is about 78%. And then you have oxygen, and then you have some other gases, the inert gases like helium and neon and so on, carbon dioxide, etc. All right. So that's also an example of a homogeneous mixture. In fact, any mixture of gases will be a homogeneous mixture. Any mixture of gases will be a homogeneous mixture. All right. Okay. So let's move on now to a discussion of the other type of mixture, which is known as a heterogeneous mixture. And as stated here, a heterogeneous mixture is basically one where the composition or properties of that mixture vary from one part to another. All right. So there are several examples of heterogeneous mixtures that exist. For example, oil and water. If you mix oil and water, we know from our everyday experience what will happen. The oil will settle at the top and the water will go below. All right. And one can see a boundary between the two. Okay, so that's an example of a heterogeneous mixture. All right. Another example of a heterogeneous mixture would be salt and pepper. And I'm quite sure you can think of other examples of heterogeneous mixtures from our everyday experiences, right? So it's very important that you know the distinction between a homogeneous mixture and a heterogeneous mixture, all right? Any questions so far? Any questions? Any questions? Okay, continuing our discussion. Again, this is something you would have met before, so I'm just going to go through this rather quickly. Chemical symbols. We all know what these represent. They basically represent elements and when combined, compounds. And as stated here, a chemical symbol is basically a 1 or 2 letter designation derived from the name of the element. In some cases, well, where you have a 1 letter representation or designation, that would be an uppercase letter, such as in the case of hydrogen. And if you have a 2 letter designation, the first letter would be uppercase and the second one would be lowercase, such as in the case of neon and chromium, all right? Now, most symbols are based on English names, right? In other words, you can basically look at the name or look at the symbol and see the relationship between the symbol and the name. And we can see that in each of these 3 examples. In other instances, the relationship between the symbol and the name is not that obvious. And the reason why is because very often the symbol in those cases will be derived from the original Latin name of the particular element. So for example, as you can see on the screen, in the case of copper, the symbol is Cu. And the reason why that's the case is because the Latin name for copper is cuprum, all right? And one can see that for the other elements in this list right here. So there are some instances where the symbol looks very different from the original usual name of the element. For example, in the case of potassium, right, the symbol is K, right? And that's because the original Latin name is Kalium right here. So sometimes you'll see that relationship between the symbol and the name of the element. Okay, now we're going to take a bit of a detour here because we're going to delve into something which is very important. I'm assuming that you all are budding scientists. So it's very important that you understand and appreciate what we call the scientific method, which is basically the method or the approach. Okay, what's going on here? Something is missing here. Okay, there should be something here. Anyway, okay, let me go ahead. So basically, the scientific method is a step-by-step description of how scientists go about investigating and understanding nature, all right, or natural phenomena. Now, the first step in this process is called the observations, right? And usually the observations that are made can be stated as a law if it is universally consistent. So for example, we all know from your introductory chemistry when you were dealing with gas laws that the pressure of a gas is inversely proportional to the volume, all right? And that law is true in all cases. It's always observed and there's no exception that one can find to that observation, all right? Now, after you have made that observation, then the next thing that you have to do as a scientist is that you have to come up with what we call a hypothesis. And what's a hypothesis? A hypothesis is basically a tentative explanation for what was observed in the first step of this process, all right? Now, this is basically something that has to be a reasonable explanation. You cannot just make up some story or say something like God did it or whatever. You have to come up with an explanation that makes sense to explain what you observe, and that would be your hypothesis. Now, in the sciences, we're not just satisfied with just coming up with a reasonable explanation, because we want to find out if that explanation is in any way valid. And the way we do that in the scientific method is that we conduct experiments in order to test the hypothesis. And this is where the bulk of the hard work of scientists is involved. Because basically what the scientists would have to do is take into account what the hypothesis says and design an experiment in order to basically tear down the hypothesis if the hypothesis is not true, all right? In other words, we want to see if the results are falsifiable, all right? Which means basically that if the hypothesis is false, then the experiment would be designed to show that it's false, all right? So this process of coming up with a hypothesis and experimentation is repeated over and over again, because usually what happens, especially in the initial steps, is that when somebody conducts an experiment to test the hypothesis, usually we find that the hypothesis turns out not to be true because you cannot reconcile the experimental data with the initial hypothesis. So what that means, therefore, is that you have to go back up here and basically make modifications to the hypothesis based on what you know of the experimental data, or come up with a new hypothesis which fits the experimental data, and then you conduct further experimentation to test that new hypothesis. So this process goes on over and over again until you have harmony between the experimental data and the refined hypothesis. And when you get to that stage where the refined hypothesis fits well with the data based on experimentation that tests the hypothesis, that hypothesis now becomes what we call a scientific theory, right? So a scientific theory is basically a well-tested hypothesis, which is based on the weight of the experimental data that was obtained as a result of conducting experiments, all right? And in fact, if the theory is worth its salt, then you can use a theory to make other predictions related to the original phenomenon, all right? Now that we have gotten to this stage, a key thing you need to remember and understand is that even though you might have a well-tested hypothesis, which is now the theory that has been widely accepted by the scientific community, that is not necessarily the end of the story, because it is possible that somewhere on this planet, a scientist might be tinkering in his or her lab to test the well-established theory. Now, in most cases, what you'll find is that further experimentation supports the well-established theory. But there are instances in scientific history where the experimentation that is conducted on the theory basically proves the theory to be false. So you might have a theory that is widely accepted by the scientific community over decades or even centuries, and then somebody out of the blue decided to conduct an experiment and come up with data which basically refutes the well-established theory. And there are many instances in science where that has happened, all right? And when that has happened, that means that you have to come back up here to come up with a new hypothesis and go through all these processes again. Now, here's one example of a situation where you have a well-established theory and then it was debunked by a scientist. And this one was quite by accident. So let me get out of this and let me do this here. Okay, so there was, and I don't remember the dates, you can look this up, a scientist by the name of, I'm going to write his name here, I think he was from Sweden, Frederick, I think this is how his name is spelled, Waller, and I think in the Swedish language, I put 2 dots here over the O. Now, he was a chemist and he was trying to make this compound, ammonium cyanate, all right? Now, he went through a long series of reactions and he ended up with this compound in an aqueous solution, all right? So typically, and this compound is ionic, and typically in chemistry, if you have an ionic compound in an aqueous solution, then to isolate that compound, what you would do is heat it to drive the water off. And this is what he did, right? So he was expecting to get a pure sample in a solid state of ammonium cyanate. However, what happened is that this compound was transformed into this compound. Write down the formula for this compound here. I'm sorry, H2NC11O NH2. All right. And the name of this compound is called urea. All right. And the urea here is a naturally occurring compound that you'd find in cows, mammals, basically any mammals, cows, goats, human beings, etc. Now, why is this important? Well, what happened is that before Frederick Wohler did this experiment, there was a scientific theory known as, oh gosh, the name escapes me now. Vitalistic theory, thank you. Vitalistic theory, vitalistic theory, all right? Now, according to this theory that existed, that was widely accepted by the chemistry community, this theory says that there are certain compounds that exist in nature that cannot be made by human beings in a lab, all right? And the reason why that is so, according to this theory, is that there's this thing out there in nature known as a vitalistic force, right? So this was a theory that was widely accepted because, of course, nobody was able to synthesize any natural compound in the lab until Frederick Wohler did this, right? He was the first person recorded to synthesize a natural compound, urea, from ammonium cyanate. And the interesting thing about this was that this was totally by accident. He didn't plan to do this. He wasn't out to try to destroy this theory. But basically, once the evidence turned up from his experimental work that urea was formed as a result of experiments that he did in the lab, then that signaled the end of the vitalistic theory, all right? So this is just one example of how a well-established theory has been accepted by the scientific community, and then somebody out of the blue comes with new information, new data from experiment, which basically destroys that theory. So the lesson that we learned from this is that when it comes to the practice of science, there's no sacred cows, right? Everything is subject to question, even well-established theories, right? And therefore, it shows you how dynamic chemistry is as a science, and science in general, right? Knowledge is always changing because people are always making new discoveries. And that's, in my opinion, the beauty of the scientific method. You know, there's no established dogma or data when it comes to experimental results or even theories that have been well accepted and established. Okay, so that's just a bit of a detour, as I said before, but it's very important that you understand basically what the scientific theory is all about. Now, there's one more thing I want to mention before we actually leave this, and it goes back to something I mentioned here when we're talking about doing experimentation to get your new hypothesis, and then you test your new hypothesis with experimentation and you go back and forth, kind of like in a circle, in a loop at this section here, right? It's very important that whenever you have conducted an experiment to test a hypothesis and your experimental data is not in harmony with your hypothesis, then it's very important that you understand that basically you need to change your hypothesis after that to fit the data and not change the data to fit the hypothesis, all right? Do not ever, in whatever scientific field you decide to enter into, right? Don't you ever change the data in order to fit some preconceived notion of what you think the hypothesis should be. One, because that's dishonest. Two, it's scientific malpractice. And three, there can be lifelong consequences of that, including jail time, believe it or not, all right? And there is an example of, let me see if I have it here. Okay, I don't have it here. Let me see if I can find it in Google. There's an example of a scientist. You know what? I'm going to look for it later on and post it online. I thought I had it on the PowerPoint slide, but I didn't. But there's an example of a scientist who was working at this college and he was accepting money from the federal government, which is what most colleges do when it comes to scientific research. They compete for federal funding and so on. And this guy was, if I remember correctly, was experimenting with HIV immunoresponses from the blood of some animal, and he basically did some fudging of the numbers. And to cut a long story short, he was investigated and he was charged federally because he was receiving money from the federal government, and he was committing all kinds of frauds and so on. And as a result, he ended up serving time. And he's just one example. And there are several other examples. I'm going to find those examples and post them in Canvas so that you guys can have a look at it. Just to underscore the importance of exercising integrity and honesty when you're doing your scientific work. So as I said before, do not change data to fit whatever your original hypothesis is. What you need to do, the proper thing you need to do in this process is that you modify your hypothesis to fit the experimental data. Okay, are there any questions? Any questions? Any questions? Okay, so let's continue. Models. We use models to basically show a picture of what molecules and atoms actually look like. So an example of a model is shown here. It's called a space filling model. The red sphere represents oxygen and the white spheres represent hydrogen. So this actually is representing the water molecule. And then for chlorine, as you should know from your previous experience, chlorine exists as a diatomic molecule, all right? So as you can see here, these green spheres each represent a chlorine atom, and both of them together represent a chlorine molecule. So we use models from time to time so that we understand the shapes of molecules, which can have a profound influence on the type of reactions that they undergo. And for those of you who have to do organic chemistry, you're going to see a lot of this, the use of models to explain chemical reactions, all right? So that's an important tool that is used in chemistry. Okay, so let's talk about scientific measurements and units, right? So we know what is involved in measurements. You use some instrument to get some quantitative measure of a particular quantity like mass, length, etc. All right? And we all know that when it comes to measurements, there are two essential pieces for any direct measurement. You have the quantitative piece, which is a number, and then you have the qualitative piece, which would be the unit. And whenever you're expressing any measurement, it is totally useless to express one without the other, right? So you cannot just basically say a measurement represented by the number 60 without considering what the units would be, right? So for example, if you're talking about somebody's wages, right? And I said that I'm paid 60. Well, what does that mean, right? Are we talking about $60 per week, or are we talking about $60 per hour? And obviously the one that's more preferred would be $60 per hour, right? So this is just a simple example to illustrate the point that it's very important that you not only include the number or the quantitative piece, but you also need to include the unit. And if you have had me before in introductory chemistry, you know that I'm a stickler for units. Whenever you're doing any calculations in any assignment or tests that I'm giving you, make sure that you include your units as a part of the whole process, all right? Because as we said here, it makes no sense you have a number expressed without the units to accompany it. Okay, so these are basically the 7 common units that are used in the SI system, right? We have the unit of length, which is the meter unit, and the symbol is shown here. We have the unit of mass, which is the kilogram unit. That's the symbol here. We have time. The SI unit is second. For temperature, the SI unit is Kelvin. For the amount of substance, the SI unit is mole. For electric current, the SI unit is the ampere unit. And for luminous intensity, the SI unit is the candela unit, and that's the symbol right here. Now, of these units in this particular course, we'll be concerned with only the first 5: length, mass, time, temperature, and the amount of substance. Now, for those of you who have to do general chemistry 2, you will meet the electric current unit ampere, and you'll also meet it when you do physics as well, all right? As far as the last one is concerned, I don't anticipate you needing to know how to use this unit in either general chemistry 1 or 2, right? So basically, these are the units that we'll be using between general chemistry 1 and 2, excepting the last one, all right? So those are the common units or the scientific units or the SI units that we in the scientific field use every day, all right? In addition to the units, we have what are known as SI prefixes. And this adds some flexibility to the metric system or the SI system, because you can use these prefixes to express larger or smaller values. As you may know from your previous experience in introductory chemistry, in chemistry, we use very, very large numbers in some cases. For example, the number of atoms in a particular sample. And in other cases, we use very, very small numbers, such as the mass of an atom, all right? So that's the reason why prefixes are also very important. So as you can see here, this is just a short list of all the prefixes. If you go to the table that I've posted in Canvas, let me show you where. So if you go to Canvas and you go to Files, and then go to Tables, and goes to Tables Chemistry, I have provided for you a more comprehensive list of all the prefixes that you're going to need. So let me make this larger. Okay, so scrolling down, we get to this page, all right? In fact, there are 2 pages. Let me turn this around so you can see that. Okay, so this is a more comprehensive list of the different prefixes. These prefixes are for smaller values, right? So deci is 10 to the minus 1, which is the same thing as 0.1. Centi is 10 to the minus 2, milli is 10 to the minus 3, and so on and so forth. And then for the larger prefixes, or the prefixes representing larger values, Geiger is a billion, 10 to the 9, mega is a million, 10 to the 6, and so on and so forth, right? So those are the prefixes, and this is a table you can refer to in order to figure out what the prefixes represent. Okay, going back to the PowerPoint here. Okay, so, oh, by the way, before I move on to the next topic, or the next page, I just want to give you an example of how we use the prefixes. So let me go back to here. Let me get a new, oh, okay. So for example, just to show you how the relationship between the basic metric unit and the prefixes, if I have 1 millimeter and I want to find out how much it's worth in meters, right? Well, according to the table here, if you go to the table, milli means 10 to the minus 3, all right? So therefore, going back to this here, since milli is equal to 10 to the minus 3, that means that 1 millimeter is equal to 10 to the minus 3 meters, right? So the milli here, the M here, represents 10 to the minus 3. Another example, kilo means 10 to the 3. So 1 kilogram is equal to 10 to the 3 grams, right? So therefore the kilo here represents 10 to the 3, all right? So that just shows you how to use the prefixes along with the basic fundamental metric unit. Okay, so with that said, let's move on now to the next slide. So we're gonna look at different types of quantities, all right? And basically the units associated with them, and the different relationships between the different types of units for those particular quantities. So the first one we're going to look at is volume, measuring volume. So volume basically, if you remember, is the amount of space that is occupied by an object. And the typical base unit that is used for volume is the liter unit, all right? So as stated here, it's very convenient for measuring the volume of irregularly shaped containers. But you can also use it, of course, for measuring or expressing the volume of regular shaped containers, all right? Now, let's look at some relationships here in terms of the units. So as we said before, the liter unit is basically a fundamental base unit, right? Now, we're using this diagram here to illustrate this point. Now, let's say you have a cube which is 1 centimeter cube in terms of volume. In other words, each length of the cube is 1 centimeter in terms of length exactly, all right? So let's say that we stack the cubes in such a way, each of the cubes having a 1 centimeter cube volume, and we have several of them. So let's say we stack them in such a way that we produce a larger cube with each length being 10 centimeters. So basically, as you go from one cube to the next, you're going to have a total of 10 cubes going this way, 10 cubes going this way, and so on and so forth, right? So therefore, what you'll find is that the total volume of this cube would be 10 by 10 by 10, which is equal to 10 centimeters cube, all right? Now, it turns out that by definition, 1 centimeter cube is equal to 1 milliliters, right? So if 10 centimeter cube, let me clean this up again. If 1 centimeter cube is equal to 1 milliliter, then 1,000 centimeters cube would be equal to 1,000 milliliters. And guess what that is equal to? That is equal to 1 liter, because milli represents 10 to the minus 3. So therefore, 1,000 times 10 to the minus 3 liters would be equal to 1 liter, all right? So that's one relationship we can establish, the relationship between the centimeter cube and the liter unit, all right? Another thing that you need to recognize is that 10 decimeter is equal to 1 centimeter. No, I'm sorry. 1 decimeter is equal to 1 centimeter, is equal to 10 centimeters, all right? So if we were to cube this and cube this here, you're going to have 1 decimeter cube is equal to 10 to the cube, which is 1,000 cm cube, all right? So here we have a relationship between the decimeter cube unit and the centimeter cube unit, which is in turn equal to 1 liter. So therefore, 1 decimeter cube is equal to 1 liter, all right? So I'm just showing you this to show the different relationships between the different units. So if you go back to the PowerPoint here, you'll see it's stated here, 1 decimeter cube is equal to 1 liter, 1 centimeter cube is equal to 1 milliliter, and so on and so forth. Okay, so any questions about this? Any questions? Any questions? Okay, another quantity we're going to look at here is the temperature, right? Now, there are 3 known temperature scales, 2 of which are shown here, okay? Now, the first one here, represented by this thermometer, is the Celsius scale, all right? The one here, represented by this thermometer, is the Fahrenheit scale, and there's a relationship between the 2, all right? The relationship between the Celsius scale and the Fahrenheit scale is given by, okay, temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32, all right? So that's a relationship between the Fahrenheit scale and the Celsius scale, all right? So as a result of that, one can see that, for example, at 0 degrees Celsius, which is the freezing point of water, right? If you put 0 here, then this becomes 0, which means that the temperature in Fahrenheit would be equal to 32 degrees, right? And similarly, if you look at the room temperature, you'll see that, which is, 20 degrees Celsius, somewhere between 20 and 25, that's usually room temperature. So let's say it's 20 degrees Celsius. Then if you plug this 20 into this equation, that works out to be 68 degrees Fahrenheit. And then here, for boiling point of water, which is 100 degrees Celsius by definition, then if you plug the 100 into this equation, it works out to be equal to 212 degrees Fahrenheit. So that's basically the relationship between the Celsius scale and the Fahrenheit scale. There's the third temperature scale, which is known as the Kelvin scale. And let me see if I have this here. Well, the equation for the relationship between the Kelvin and the Celsius value, the temperature in Kelvin is equal to the temperature in Celsius plus 273, all right? And there's a bit of history behind that, which we'll get into later on when we start talking about the gas laws. I won't go into that right now, but for now, you need to keep this in mind, right? So this is the relationship between the Fahrenheit and the Celsius unit, and this is the relationship between the Kelvin and the Celsius unit, all right? Okay, so that's basically as far as the temperature scales are concerned. Now, let's talk about the difference between precision and accuracy when it comes to measured values. Now, precision, and by the way, people use these terms in everyday language as if they mean the same thing, but they're two different things, all right? Even though they might be related to each other. So, precision. What is precision? Well, precision is referring to how closely individual scientific measurements agree with each other. Excuse me. All right, so what that means basically is that if different people use the same instrument to measure a particular quantity, like for example, use the balance to measure, let's say, a sample of sodium chloride, then how close these measured values are to each other is a reflection of how precise the measurements are, all right? Now, accuracy is something different. Accuracy refers to the closeness of an average of a set of scientific measurements and compared to what is called the correct or most probable value, right? So if, let's say, going back to the example I mentioned previously, let's say there's a known value attached to the mass of a sample of sodium chloride, then how close the measured values to that known mass is basically a reflection of the accuracy of these measured values. Excuse me. Okay, so that's the difference between precision and accuracy. And then when it comes to measurements, you can have what are known as sampling errors. And these occur when you have a group of scientific measurements that do not represent the entire population, right? So this is something that is very important, especially when it comes to statistical data. You have to make sure that whatever sample that you're using must be representative of the whole, so that whatever measurement that's associated with that sample is reflective or a reflection of the whole. Okay, so that's basically what precision and accuracy and sampling error is all about. Now, to illustrate this further, what we're going to do is look at this example here. So what we have here is a dartboard, and of course, if anybody plays darts, you know that you get 3 attempts at scoring. So that's why we have 3 darts, right? So basically, each attempt in this particular illustration is representative of an act of measuring something, all right? And the center here represents a true value, okay? So if you look at this first example right here, you see that the darts are all over the place, but they're far from each other, and they're nowhere near the middle, right? So what that means, or what this represents, I should say, is that in terms of measurement, this represents low accuracy and low precision. Low accuracy because these darts are nowhere near the middle, and low precision because the darts are far away from each other. Then we get to this situation where the darts are close to each other, but they are far away from the middle. So this represents a situation of low accuracy and high precision. Why? Because it's low accuracy because the darts are far from the center, and high precision because the darts are close to each other. And then we have a situation where the darts are relatively close to the center, but they're far from each other. So this represents a situation of high accuracy and low precision, right? High accuracy because the darts are close to the center, but the precision is low because the darts are far from each other. And then this represents the ideal situation, high accuracy and high precision, where all the darts are bunched together at the center of the dartboard, all right? And this is basically what we aim for when we're doing any experimentation. We're aiming for high accuracy because we're trying to get the true value. And also, if the accuracy is high, we're hoping also that represents high precision, which means that the values will be close to each other. Okay, so that's basically the illustration of high precision and high accuracy. Now, when it comes to reflecting precision, which of course comes from direct measurement, what we do in order to have a measure or feel for the level of preciseness of a measurement is that we look at what are known as the significant figures being expressed in that measured value. So when we're talking about the significant figures in a measured value, we're talking about all the digits in a number that are known with certainty plus the first uncertain digit, all right? All the digits in a number that are known with certainty plus the first uncertain digit, all right? Now, let me explain what we mean by that. Basically, well, for one, let me just say up front, this concept of significant figures applies only to measured values, right? And the more significant digits that you obtain from your measurement, the better will be the precision of the measurement. So more significant digits equal to greater precision in the measurement. Exact values. These are basically numbers that have an unlimited number of significant figures. And there are two types of exact values. You can get exact numbers or values by either definition or by counting. So for example, the number of students in a class, that would be whatever that number is. If there are 10 students in a class, then that 10 would be an exact number. It's not a measured value. You did not measure that number, or you did not measure anything to get that number. You basically do a head count of the students in the class, and that would be that number, and it's exact. An example of an exact number obtained by definition would be, for example, 100 centimeters is equal to 1 meter. Now, this relationship is by definition. All right? And because it's by definition, that means that these numbers here, the 100 here and the 1 here, would be exact numbers. All right? So those are the only two types of exact numbers, and these numbers have an infinite number of significant figures, right? Measured numbers, on the other hand, have a finite number of significant figures. But the greater the number of significant figures in a measured value, the greater the level of precision represented by that value, all right? Now, let me illustrate or explain further. Okay, oh shoot, okay, I'm missing a diagram here. Let me just check something here. Okay, I'm missing a diagram here, and it was very important. I'm sorry about this, folks. Let me escape this here. Okay, where is it? Where is it? Let me go to here. Let me go here. Let me close this. Okay, I'm sorry about this, folks. I thought I'd placed the diagram which illustrates how we get the number of significant figures from a measured value. So I have to find a PowerPoint from my introductory class. So some of you may have seen this before. Let me go here. Go here. Okay, let me scroll down. Okay, here it is. Okay, so what we're going to look at is using a thermometer or reading a thermometer. And what I'm going to show you is how do we get the number of significant figures, the appropriate number of significant figures directly from reading an instrument like a thermometer. So here we have 3 thermometers side by side. And they represent different measurements in terms of where the mercury level is. Now, for the first 2, these 2 on the left, right, you'll notice how the stem of the thermometer is graduated, right? You have 20 here, you have 30 here, right? So that's 20 degrees, that's 30 degrees, right? And you have 10 individual marks between those 2 values, right? So obviously that means that this mark here represents 21 degrees. This mark here represents 22 degrees, and so on and so forth, right? And the same is true for this thermometer right here, all right? Now for this thermometer right here, the graduation marks are a bit different because you do have these marks here, which are similar to the ones that we see here, but you have some finer divisions right here between, for example, 20 and 21, right? So each of these markings represent 0.1 degree, all right? So what you're going to see is that the type of graduation that is shown here for these different thermometers will have an influence on the level of precision represented by the mercury level where it reaches. All right, so let's start with this one right here. So the mercury level here is just above the 21 mark, right? So we know that the temperature being represented here would be 21 point something, right? So the question is, what is that something? What is that digit that comes right after the decimal point? So a reasonable person could look at this and says, well, I think this is 21.1. Another person could look at this and say, no, I don't think so. I think it's 21.2. As far as I'm concerned, both persons are right, because basically what you're forced to do is to estimate what that digit is after the decimal point. So it could be 21.1 or it could be 21.2, right? In this case here, it's 21.2. But as I said before, if I were to grade something like this and somebody said 21.1, I would give them full credit, right? And the reason why is that the 2 here, or the 1 that comes after the decimal point, is an estimation, and therefore that 2 is uncertain. So therefore the total number of significant figures represented here will be these two digits that we're certain about, plus this digit that we are uncertain about. So therefore the total number of significant digits here would be 3, all right? Okay, so let's look at this middle thermometer right here. Now in this case here, the mercury level seems to be just at the 22 mark, right? But because the spacings here are the same as the spacings here, the level of significance must be expressed identical to the one that was expressed here. In other words, we have to express this to the level of the first decimal place. So by my estimation, this will be 22.0, all right? Because you're certain about these 2 digits, the 2 and the 2, but you're uncertain about the 0 because again, that would be an estimated value for the same reason as we saw in this case. So again, the number of significant figures reflected here would be 3 significant figures. Okay, now let's get to the last thermometer right here. And in this case here, we notice that, as we said before, we have smaller divisions. So looking at this here, we know that this is 22.1 something, right? We're certain about the 22.1. What we're not certain about is the digit that follows the 1 that's occupying the 100th place in the number. So one could look at this and say, well, I think it's 22.11. Another person could say this is 22.12. Both persons are right as far as I'm concerned, because we have to estimate this digit here, the second decimal place, right? So in this case here, the total number of significant figures here represented would be 4 significant figures, right? We're certain about these 3 figures here, the 2, and the 1. What we're not certain about is this 1 right here. So we have 4 significant figures represented in this number, all right? So I thought it was important for me to go through this so that you understand how to derive the correct number of significant figures when you're doing experiments. For example, if you're doing a lab, you will have a similar type of scale on different instruments, such as a burette. So if you're doing a physical lab, you have to know how to read the scale properly so that you can record the correct number of significant digits. Okay, so let me go back to the original PowerPoint. And let's deal with some rules concerning sig figs. And I think this will be the very last thing we're going to talk about today. So what we're talking about here are the rules that govern how to determine the number of sig figs if you're given a measured value in a question, for example. So let me skip this. Okay, so here are the rules. Let me see here. You know what? Let me leave this here and go to another, actually the same PowerPoint, because I think the rules are demonstrated. Okay, let me use this here. I'm going to include this in the original PowerPoint and post it online. So these are the rules for determining the number of sig figs in a measured value, right? So the first rule here is that all non-zero digits are significant, right? So all digits from 1 through 9 should be considered significant if they're indicated in a measured value. So here's a simple example, 461, that represents 3 significant figures, all right? Now, all the other rules that we're going to discuss deals with zeros in a particular situation. Okay, so this rule says a 0 is significant when it is situated between non-zero digits, all right? So here's an example, 401, all right? The 4, the 0, and the 1 are significant. The 0 is significant because it's sandwiched between the 2 non-zero digits, all right? Here's another number, another example. And in this case, you'll notice there's a decimal point there. That doesn't make a difference. As long as you have zeros sandwiched between 2 non-zero digits, then those zeros are significant. So we have basically 5 significant digits shown here, all right? Here's another example, 9.03. Again, the 0 is sandwiched between the 9 and the 3. Even though you have a decimal point here, that makes no difference. That 0 is significant, all right? Okay, now this rule has to do with a situation where you have zeros at the end of a number and there's a decimal point present anywhere in that number. So basically what this rule says is that if you have zeros at the end of a number and you have decimal point anywhere in the number, then those zeros are significant. So this number here, represented here, has 5 significant digits. All right, here's another example. In this case here, this 0 here is significant because you have a decimal point here. So this 0 at the end here would be significant. So again, we have 5 significant digits represented here. Now, this rule deals with a situation where 0 is not significant, and that is when it appears before the first non-zero digit. So let's look at this number here. So you'll notice that you have 3 zeros and then you have a 6 here. These zeros are not significant, right? And that's because these zeros are preceding the first non-zero digits, all right? Here's another example. This 0 is not significant because it precedes the first non-zero digit. But this 0 is significant because it is sandwiched between 2 non-zero digits. Okay, here's another situation where a 0 is not significant, and that is when it is at the end of a number where there's no decimal point. All right, so if you look at this number here, there's no decimal point in this number. So what that means is that all these zeros are not significant, which means that this 5 here would be the only significant digit. Okay, here's another example. Okay, so in this case here, no decimal point. This 0 is at the end of the number. So therefore, that 0 is not significant. So therefore, we have 4 significant digits represented here. Okay, all right. I think I'm gonna stop here for today. So the next topic we're going to discuss is how do we, let me just check and make sure. Hold on 1 minute. We're going to talk about how do we deal with significant figures when it comes to calculations, all right? Okay, let me see here. Okay, so that's basically it for today. Are there any questions you have for me? Any questions? No questions? Okay, so if there are no questions, that's basically it. So I'm going to see you guys on Thursday, and we're going to continue our discussion. All right? So take care and have a good day. See you Thursday.